Good morning, dear student. In previous lecture, we already discussed about lability and inertness on the basis of VBT. So, according to VBT, the outer orbital complexes those shows sp3 d2 hybridizations are labile, while the inner orbital complex d2 sp3 may forms labile or inert complex. So let's discuss. So in today's lecture, we are very much interested to find out the labile and inert complex, lability and inertness of the complex on the basis of CFT, that is crystal field theory. So to understand this point, that is lability and inertness on the basis of CFT, you should must know that if you consider the octahedral complex, whenever we consider the octahedral complex, this octahedral complex react either either by Sn1 Sn1 or Sn2 mechanism, Sn1 or Sn2 mechanism, either by Sn1 or Sn2 mechanism. So you are very much familiar with this Sn1 or Sn2 in organic chemistry. So the Sn1 and Sn2, the meaning is uh, the principle behind this Sn1 and Sn2 is same in inorganic chemistry for octahedral complex. That is, this octahedral complex react either by Sn1 or Sn2 mechanism, in which, if you consider, this complex react either by Sn1 or Sn2 mechanism, in which the intermediate, in which the intermediate are five membered, five membered, and the intermediates are five membered and seven. Okay, the intermediates are five and seven coordinated species, seven coordinated species, seven coordinated species respectively. Okay, so whenever we consider the octahedral complex, it shows two type of reaction, that is Sn1 or Sn2. So we already discussed that Sn1 is nothing but your dissociative type of mechanism. So at least you should understand what is this Sn1 mechanism. It is a dissociative type of mechanism, dissociative type of mechanism. So for whenever there is a substitution, whenever there is a substitution reaction to occur, or whenever there is a replacement of ligand in Sn1, there is a dissociation. The first step is dissociation, and the rate determining step is dissociation, because the octahedral complex containing total 6 ligand. So for substitution, so one of the ligand must be dissociate from this octahedral complex. So what happen, when one of the ligand is dissociated from this octahedral complex, the coordination number of this complex is decreases by 1 unit. So whatever the complex, that is octahedral complex, in which the coordination number is 6, then it is converted into coordination number 5. So the coordination number of intermediate is decreases by 1 unit, and it is 5. So this is for Sn1. If you consider the Sn2, then it is associative type of mechanism. So associative type of mechanism. So in this case, for substitution, the incoming ligands attach uh, to this metal atom before displacement of any other ligands, and therefore what happen, so initially the coordination number is 6, but when these incoming ligands it will forms the bonds with metal atom, then the coordination number is increases, and we get 7 coordinated intermediate. So in this case we get 5 coordinated intermediate, 5 coordinated intermediate for dissociative type of mechanism, and for associative we get 7 membered or 7 coordinated, 7 coordinated, 7 coordinated intermediate. 7 coordinated intermediate. So you should keep in mind, whenever we consider the octahedral complex, it will react either by Sn1 or Sn2 mechanism, in which the intermediates are 5 and 7 coordinated species respectively. So Sn1, it is dissociative type, and Sn2 is your associative type. In Sn1, the intermediate having coordination number 5, in Sn2 the intermediate having coordination number 7. Okay. If you consider in both the cases, that is in Sn1 or Sn2, the symmetry of the complex is lower. The symmetry of the complex is lower down due to the change in crystal field symmetry, and the CFSE, that is crystal field stabilization energy, is also changed. So you should keep in mind, in both cases, the symmetry of the complex is lower down. The symmetry of complex is lower down. The symmetry of the complex is lower down due to this change in crystal field symmetry. Due to this change in crystal field symmetry, the CFSE value is also changed. That is crystal field stabilization energy. CFSE value is also changed. The CFSE value is also changed. Okay, so let us discuss what is labile and inert complex according to this crystal field theory. So at least you should know this point. Okay, let us discuss the next one, that is, so the first one, that is a labile complex according to CFT, which is a labile complex. So labile complex, that is, if the CFSE value, so according to CFT, if the CFSE value, that is crystal field stabilization energy value, for 5 or 7, means either Sn1 or Sn2, 5 or 7 membered intermediate, 5 or 7 member intermediate complex is greater than that of reactant. So whenever the CFSE value for 5 or 7 membered intermediate complex is greater than that of reactant, the complex will be labile complex. So according to the CFT, whenever the CFSE value for 5 or 7 membered intermediate complex is greater than that of the reactant, means the reactant having coordination number 6, okay, the complex will be labile. The complex will be labile as there is zero activation energy barrier. Zero activation energy barrier. So according to this CFT, crystal field theory, so you should keep in mind this point. Okay, so CFSE value for the intermediate, either it is 5 or 7, is greater than that of reactant, the complex will be labile as there is a zero activation energy barrier. So let's discuss about the inert one. Let us discuss about the second, that is inert complex. So if the CFSE value for this, if CFSE value for 5 or 7 member intermediate intermediate complex intermediate complex is less than that of reactant than that of reactant than that of reactant than that of reactant, the metal complex will be inert in nature. The metal complex will be inert in nature. The metal complex will be inert in nature. Okay. Here you should keep in mind, hence the gain of CFAC, when the CFAC will be more or it is increases, then the complex will be labile, and the loss of CFAC will make the complex inert. So finally you should go to the conclusion that the gain of CFAC, so whenever the CFAC of the intermediate is greater than that of reactant, then the complex is labile. Means the gain of CFAC, that is CFAC value is increases, crystal field stabilization energy will be increases. So gain of CFAC make the complex labile, and the loss of CFAC okay, the loss of CFAC means the intermediate having lower CFAC value as compared to reactant, the loss of CFAC will make the complex inert. Okay, and the calculation of this crystal field stabilization energy rely upon the following assumptions. So how one can find out the crystal field stabilization energy for this substitution reaction, either it is Sn1 or Sn2. Okay, so let us discuss about this CFAC. Okay, so the calculation of CFAC, so you should keep in mind the calculation of CFSE, crystal field stabilization energy, rely upon following assumption. So what are these assumptions? Let us discuss the first one, that is all the 6 coordinated complex should be treated as perfect octahedron. So all 6 coordinated, so whatever the reactant complex is there, all 6 coordinated complex, it is considered as a perfect octahedron. No doubt the ligand is different, that is even if the mixed ligands are present. So okay, the ligands are not same, or the mixing of ligand is there, that is some ligands are different, some ligands are different, then all 6 coordinated complex are considered as a perfect octahedron. The second important point is that is delta octahedron or DQ parameter in this octahedral complex. Okay, so delta octahedron or 10 DQ magnitude for the reacting as well as for reacting, the magnitude, that is delta octahedron magnitude for reacting as well as intermediate complex, are assumed to be same, okay, are assumed to be same. So we consider the delta octahedron 10 DQ magnitude for reacting species, that is for reactant as well as the intermediate complex assumed to be same. The next one, that is the third assumption, is that the JTT, the capital JTD means the John Taylor distortion, the capital JTD capital J T D, that is John Taylor distortion, should be neglected in all calculation. So JTT will be neglected, will be neglected in all calculation. So these are the important assumptions to calculate the CFSE for for lability on inertness on the basis of crystal field stabilization energy, on the basis of this CFT, that is crystal field theory. Okay, so let us discuss for the either it is Sn1 or Sn2. Okay, so how one can find out CFSE, that is gain or loss. Okay, so let us see the first one, that is for uh, Sn2 means it is associative type, in which coordination number of intermediate is increases by 1 unit. So in this case we get 7 coordinated intermediate, and the 7 coordinated intermediate may be pentagonal bipyramidal. The 7 coordinated intermediate may be pentagonal bipyramidal or cap octahedron. Okay, so 7 coordinated intermediate having a geometry of pentagonal bipyramidal or cap octahedron. However, it has been observed that for associative mechanism to occur through octahedral wedge or cap octahedron intermediate, the gain or loss of CFSE can be calculated as, okay, so we are considering the cap octahedron, okay, or it is also called as a wedge, okay, wedge or cap octahedron. So CFSE, okay, for Sn2 it is associative 7 coordinated intermediate having two geometry, one is pentagonal bipyramidal and second is cap octahedron. So for associative mechanism occur through cap octahedron intermediate, the gain or loss of CFSE gain or loss can be calculated by using this formula, that is CFSE of octahedral wedge, that is octahedral cap intermediate, octahedral cap intermediate minus the CFSE of octahedral reactant, so we can find out the CFSE for octahedral wedge intermediate minus CFSE of octahedral reactant. Similarly for Sn1, if we consider for Sn1 mechanism, that is it is your dissociative type, in which the coordination number is decreased by 1 unit, that is the intermediate having coordination number is 5. And if you consider for Sn1, it is dissociative type, it will shows 5 coordinated, and it may be either trigonal bipyramidal or square pyramidal, geometry for coordination number 5. So it may be trigonal bipyramidal or square pyramidal. However, it is observed that the dissociation mechanism occur through square pyramidal intermediate. So whenever there is a dissociation, it is occur through square pyramidal intermediate, and hence the gain or loss of CFSE, so CFSE gain or loss for this Sn1 type of mechanism can be calculated by using this CFSE of square bipyramidal. It is square pyramidal, not bipyramidal. It is square pyramidal minus square pyramidal intermediate minus CFSE of octahedral reactant. So you should find out the CFSE gain or loss for this Sn1 and Sn2. So for this you should find out the CFSE value for this octahedral cap octahedron, that is octahedral wedge intermediate, and the CFSE value for square pyramidal intermediate. Okay, so if we find out this value, then we can easily find out the CFSE gain or loss. Okay, and we already know that is gain of CFSE, which results into the what, whenever there is a gain of CFSE, make the complex labile, and the loss of CFSE make the complex inert. So when you should know this value, CFSE of square pyramidal and CFSE of octahedral wedge intermediate, then one can easily find out CFSE gain or loss. But this is very complex. So in the next lecture, I will give a value, okay, for different d1 for different d configuration. So you just remember these values, and you just remember which configuration is labile and inert. So we are not very much interested to find out the CFSE for square pyramidal and CFSE for the octahedral wedge intermediate. So it is very complex, so we are not very much interested into this. So in the next lecture we're discussing about some tables and the values, that is we can easily find out the gain or loss, that is these values are given for different configuration, and on the basis of these values one can easily predict that is this configuration is labile and this configuration is inert. So this is all about the lability and inertness on the basis of CFT. In the next lecture we discuss about we discussing these values, and we discuss the mechanism of associative as well as dissociative type of substitution reaction. Thank you.